Hey guys, welcome to our new course, Spacecraft Design and Engineering, provided by Astrogen. I'm Shushanth, and I'm going to be walking you through a whole vast variety of topics throughout these lectures regarding spacecraft engineering, the historical milestones we've had, propulsion technologies, etc. It'll be really fun. So first up, this is going to be a very introductory lecture. We're going to go into more of the history of spaceflight, why it's important, things like that. So our first topic on the agenda is the overview of global applications of rockets and spacecraft. So we're basically going to go over why spaceflight is important in the modern day. And a lot of people might ask, why are we sending billions of dollars in taxpayer money over to NASA and all of these private companies? Well, there is a good reason for that, and you'll see in a minute. Then we're going to go into the historic milestones in rocketry and spaceflight. So basically, what kind of accomplishments have we done since the 1950s in terms of advancing spaceflight forward? And then we're going to look at current industry trends and look at possibilities for future growth of our global space programs. All right, so let's get into it. First off, we're going to go into why space exploration matters. First off, we're going to go ahead and list all these technologies that we have gathered because of spaceflight exploration. The first and foremost is GPS. The growth of satellite technology since the 1960s has allowed us to develop things such as GPS, which we obviously use on an everyday basis. If you use maps for driving or geopositioning, it's basically necessary for a lot of other technologies to take place. So here's kind of a basic rundown of how it works. Essentially, it depends on a system of at least 24 satellites in orbit. And so you need 4 of those satellites for each user who is basically trying to find their own position on the ground, right? So what happens is, by using the latency of the signals that are being transmitted from the satellites to the user, you're able to find the exact altitude, longitude, and latitude of the user just based on a mathematical process called triangulation. It's a pretty complicated process. Don't want to get too much in the specifics of it, but it's one of the main technologies that has arisen out of our ventures. Next is advanced water purification and filtration technology. This has a variety of uses. We often see water purification being utilized for places on Earth that don't really have access to clean water. And this is especially important. And this technology is being utilized in the ISS to a very great extent. They recycle almost 98% of the water that they take in. And the reason why they have to do this is because it's very expensive to be taking up payloads into low Earth orbit. It costs thousands of dollars per each kilogram. So one of the things that the space programs have tried to do is minimize the amount of water they have to take up so they can replace it with more valuable goods. Next, we're going to go into pharmaceutical production for medicines. And this right now is currently undertaken by companies like Varda Space. I'll get into more details about them in a minute. And then lastly, this might seem basic, but it involves a lot of technological progress, and a lot of it has been done through spaceflight. Emergency blankets, the ones that keep you warm, that are designed to keep you warm on camping trips, in case of emergencies, things like that. They're actually derived directly from the spacecraft insulation. Because remember, spacecrafts in space have to undergo extreme temperature differentials, especially once they're orbiting as planet. On, for example, the daytime side of Earth, they'll be exposed to hundreds of degrees of heat, direct heat from the sun. While on the night side, if their orbit is on the nighttime side of Earth, they'll be experiencing more frigid temperatures. So there's a huge temperature differential, and insulation in spacecraft is key. So here's some pictures of what I was talking about before. Down on the bottom left, we see a GPS satellite. So right here, the main body, the rectangular section, that's called the satellite bus. Contains all the avionics, instruments, and other hardware that is necessary for the functioning of the satellite. These appendages on the side, these are solar panels that are necessary for power generation in low Earth orbit. Right here is an example of an emergency blanket that I was talking about before. And up here on the top left, we see a re-entry capsule that's coming in through Earth's upper atmosphere. This right here is a concept that Varda Space is currently testing. They plan on manufacturing medicines in orbit in the absence of Earth's gravity, which would allow them to do a lot more than what they can do on Earth because we're restricted in our manufacturing techniques by the presence of gravity. Although it might seem trivial, there's actually a lot more you can get done in a microgravity environment. And so what they plan on doing is essentially manufacturing some medicines and pharmaceutical products in space and then shipping them back down to Earth utilizing these re-entry capsules, which have a heat shield and a container with the goods. And right here on the right, we see a diagram for the water purification systems that I was talking about earlier. This one specifically for urine. So essentially, they take the wastewater, they send it through a distillation assembly that utilizes a variety of filters. Then they heat the mixture, and then this water is directly rerouted back to the astronauts for their use. Well, the solids are filtered out. Okay, now let's go on to the space exploration milestones. This is pretty interesting. So we're going to start with the German V-2 missile. This was manufactured in Germany during World War II, and this was the first rocket to pass the Kármán line, which is set at 100 kilometers and marks the boundary between space and the atmosphere. Though that's not really true, because the atmosphere actually extends so much further than that. But this is a point where individuals around the world have decided this is the boundary between Earth and space. So they passed that Kármán line during a photography mission. And right here, a next milestone is Sputnik 1. This was the first satellite to actually reach orbit, and it was launched on the R-7 rocket in 1957, which is still used today to launch the Soyuz missions from Russia. And today it's called the Soyuz FG, but it's still the same variant of the R-7 rocket that was used for so many decades prior. Then we have Yuri Gagarin, who piloted the first manned mission to reach orbit in 1961, before the Americans did, even with Friendship 7, like for the objective of going to space. Then we have first orbital rendezvous. So a rendezvous maneuver is basically where you have two spacecrafts that are able to meet up in orbit. So that requires oftentimes one spacecraft to be in a lower orbit and one in a higher orbit. And there's a bunch of orbital mechanics involved, which I will go into in a future lecture. But this is a very complex process, and the only reason we were able to land on the moon using the design with the Apollo capsule and the separate lander is by mastering orbital rendezvous. And this would allow us to basically embark on a whole other array of missions, like the ISS, for example. Then we have the lunar landings of the Apollo program, which we obviously know. Neil Armstrong was the first person to set foot on the moon, and this was a historic moment because it was the first time a human has set foot in another celestial body. Then we have the first space station, Salyut 1, which was launched on a Proton rocket from Russia in 1971. Sometime before the US would be able to launch their own space station, Skylab, in 1972. Here we have a few pictures of what I was talking about before. So this right here is Vostok 1. This is Yuri Gagarin's mission to reach orbit, and it was launched upon the R-7 rocket, and the capsule was in this payload fairing up here. As you can see, this right here, this is the modern Soyuz FG rocket. And if you look closely, you'll see there's a ton of similarities between this rocket and the rocket that we have flying today. The core stage, the first stage with the liquid fueled boosters and main core, is basically the same as it was before. It's just that now we have an expanded third stage. And I'll explain why we have rockets that stage and separate off boosters and other stages as well in a future lecture. You'll just have to wait to see it in a little bit. But yeah. Okay. Right here in the bottom right-hand side, you see the German V-2 rocket, which ran on liquid oxygen, and it also ran on alcohol, which led to some interest from terrible accidents at one point in history. But yeah, and also one more thing, it ran on the A7 engine, which would turn out to be the engine that basically US and Soviet engineers based their work off of. Right here in the bottom left, we see Salyut 1 and a Soyuz vehicle docking to the space station right here. And up here in the top right, I have Skylab. I posted this picture of Skylab. And this was actually launched on the same Saturn V rocket that took people to the moon. It's just that the third stage of the rocket, which would have been used for translunar injection, was utilized as a space station instead. All that tank volume was converted to be a space station. Let's keep going. So some other milestones are Viking 1, which is the first successful Mars landing by a probe, which happened in 1976. And this right here is Viking 1. It actually came with more than a lander. There was also an orbiter involved. There were some other spacecraft attached to it, but this is the main lander that descended to the surface. Pioneer 10 was the first probe to enter the Jovian system and image Jupiter and its satellites. And this right here is a render of the Pioneer 10. The STS program, also known as the Space Shuttle program, was the development of the first partially reusable spacecraft in the late 1970s and in the early 1980s. Then we have the Hubble Space Telescope. This is very important. This telescope has been utilized for so many astronautical studies and is been one of the most valuable pieces of hardware we sent up into space, and it's depicted right here. Then we have the construction of the International Space Station, which in its early stages in 1998 kind of looked like this. So this right here is the Zarya module, launched from Russia. It's a Russian module, and this right here is Unity, launched by an American space shuttle. So this was the beginning of an international partnership that will last for over 25 years, as the ISS still continues to operate today. And nowadays, the private sector, through the NASA's Commercial Crew Program and the Commercial Cargo programs, have grown, with companies like Blue Origin, Sierra Space, and SpaceX entering the market. Up here in the top right is a spacecraft known as Dream Chaser. This one specifically called Tenacity. And so Sierra Space is the company behind this. They essentially plan on making a reusable spacecraft that can launch to the ISS for resupply missions, and hopefully one day launch cargo, both crew and cargo, to the International Space Station or other stations in the future. Also, right now, the Artemis program has become the US's first step towards a sustained lunar presence. Whereas we went to the moon for temporary landings in the late 1960s and 70s, the US now plans to establish permanent lunar bases, eventually in the 2030s. So that'll be pretty cool. And then, one of the other things that's happened is we've had interplanetary missions as well, such as the Mars 2020 with the Perseverance rover that have been carried out. So right here is a picture from a satellite of the International Space Station as it stands currently. It's had a ton of changes from the previous picture I showed you, which just shows how much international and private industry efforts have been put into constructing a station. Going into detail about the Artemis program, so these two pictures are development of the human landing systems, basically the next generation of lunar landers. They're developed by Blue Origin and SpaceX. So this left one right here, this is SpaceX's Starship vehicle, which is its own vehicle in its own right, but they're going to be modifying it for lunar landing purposes in this form. And then Blue Origin's making a dedicated lunar lander running on hydrogen and liquid oxygen. And just to mention, the SpaceX lander utilizes liquid methane and liquid oxygen. So both of these vehicles are going to be utilizing new refueling technologies that we have not attempted before in space. So that's a very exciting development. Next, the Orion capsule. This was developed during NASA's previous Constellation program, which was the precursor to Artemis for lunar exploration. And so right here, this is a model of the Orion spacecraft that's being built in conjunction between NASA and the European Space Agency. Then we've also had the Space Launch System, the SLS rocket, based on shuttle-derived components being built. And we've also had international collaboration being a key factor in the construction of the Gateway space station. Gateway is meant to be a new space station that's going to be constructed around lunar orbit. Specifically, it's going to be in an orbit called NRHO, Near Rectilinear Halo Orbit. And it's going to be built in conjunction with ESA, JAXA, the Canadian Space Agency, who are going to build all of these different modules and assemble them in lunar orbit. Okay, so that's about it for all the content of Lecture 1. So now I'm just going to go into a preview of what Lecture 2 is going to be about. In the next lecture, I'm going to talk about the physical principles of what makes rockets function, look at the design considerations involved due to these factors. And this involves terms like specific impulse, delta V, and Tsayulovsky's rocket equation. So yeah, these are very interesting concepts. Make sure you stay tuned, and thank you guys for listening.